You know how Emad Mostic famously calls AI compressed intelligence? Well, let's talk about what that compression actually looks like, right down at the bare metal hardware level. We're going to kick off this explainer with a stat that is, honestly, pretty staggering. 80 to 90%. That's the percentage of modern AI compute cycles that are, well, they're actually just hardware-level approximations. They aren't exact mathematical truths. When massive language models and complex digital systems are doing all their heavy lifting, they're fundamentally just guessing the nearest answer. It completely exposes the bare metal proof of FPU stochasticity. Just let that sink in for a second.
The Great Hardware Heist: Escaping the FPU Gambler. Today, we're unpacking an absolute tech thriller. We're going to completely shatter this myth of perfect computing, and we'll look at how some incredibly brilliant developers are pulling off, quite literally, a mathematical heist. They're tunneling right under the physical limitations of computer hardware to restore absolute digital truth. So if you've always thought computers were these flawless, perfect calculating machines, oh man, prepare to have your assumptions totally challenged. Section 1. The Combatants, Gambler versus Surveyor. To really grasp this hardware heist, we've got to look deep inside the physical brain of the computer, where there's this massive, ongoing turf war happening right inside your microchips between two radically different processing components. Okay, so on one side of this hardware divide, we've got the floating point unit. Our sources perfectly call this the FPU gambler. It is incredibly fast, but it's wildly probabilistic. It's basically throwing darts at a dartboard to approximate complex numbers. And to get that blistering speed, chip manufacturers literally burn secret proprietary seed tables directly into the silicon. But on the exact opposite side, we have the arithmetic logic unit, or the ALU surveyor. Now, the surveyor is a bit slower, sure, but it deals in perfectly deterministic, undeniable facts. In the ALU's world, 1 plus 1 equals exactly 2. Every single time, on every single machine on Earth, no guessing allowed. As our source material from Kyle McLean-Smith points out, and I quote, "It's fundamentally an approximation system, not real arithmetic." Because the FPU relies on those hidden proprietary hardware tables we just talked about, your computer's approximation of a complex equation might actually be slightly different, way down in the decimals, than my computer's. It completely lacks hardware-level consistency. So perfect universal math? It's actually a total illusion when you're relying on the gambler. Section 2. The wood chipper effect. So what actually happens when we feed highly sensitive data into this probabilistic machine? Well, it shreds the provenance completely. Here is how this devastating effect builds, step by step. Step 1. The AI ingests exact source data. Let's say it's a copyrighted book or a critical financial ledger. Step 2. The FPU hardware encounters that complex data and approximates the math using those secret silicon tables. And step 3, because that math was just a lossy guess and not a precise calculation, the original data's provenance is irreversibly shredded. The gambler acts like a giant blender. Think about it. You know exactly what fruits you put into the blender, but because of those non-deterministic approximations, you absolutely cannot reverse engineer that smoothie back into the exact original fruits. The chain of title is just obliterated. Section 3. Hitting the trig wall. This flaw becomes incredibly dangerous for advanced AI or decentralized finance protocols, turning into an insurmountable FPU roadblock. So what is the trig wall? It's basically the critical failure line where errors violently compound. Think about how an AI tries to map concepts or how an automated market maker tracks liquidity. They use these smooth, continuous curves and heavy trigonometry, things like cosine scoring. But computer hardware is made of rigid, discrete squares, bits. When you force the FPU gambler to guess how to fit a perfectly round, continuous curve into a discrete digital square, those microscopic approximation errors violently compound. Under market stress or really deep reasoning tasks, you hit this critical failure line, and the system just collapses under its own mathematical weight. When you map this whole issue onto strict environments like blockchains, it is a complete nightmare. On one side of the equation, you have the Ethereum virtual machine, or EVM, which natively rejects floating point math entirely. If you try to approximate those curves on-chain, you're going to cause severe gas spikes and, worse, open the door to nasty rounding exploits. On the other side, WebAssembly environments enforce strict determinism by blocking native FPU instructions altogether. This forces developers to use what's called soft float, software emulation, which, guess what, introduces severe toolchain challenges and ABI mismatches. It's incredibly heavy, it's inefficient, and it really feels like the hardware is actively fighting the math. But if the trig wall is blocking our progress, how do we fix it? That brings us to our climax, Section 4, the square root integer hack, where developers bypass the gambler entirely using ancient number theory. Fascinatingly, developers solved this by completely ditching that gas-heavy floating point math. In GitHub repositories like amtest and square root integers, they essentially resurrected ancient math using Pell-Lucas numbers. They figured out a way to use a single linear integer recurrence to literally trick the computer into calculating nearly perfect irrational square roots using strictly whole numbers. They completely bypassed the trig wall by moving to division-free integer geometry. Basically, they forced the math strictly into the realm of the exact ALU surveyor, leaving the guessing gambler completely out of the loop. And the efficiency gains here, they are absolutely staggering. We're talking a 74 times reduction in metabolic energy. By shifting from those lossy, complex approximations of the FPU over to the pure, discrete logic of the ALU, using this integer geometry, they achieved a massive reduction in power consumption. The energy required to perform these exact geometric operations drops to an absolute physical hardware floor of just 0.05 picojoules per operation. I mean, this isn't just an iterative update, right? It's a fundamental paradigm shift in how we command silicon. Section 5, restoring absolute digital truth. Because this is about so much more than just saving power. It's about fundamentally changing the accountability of our digital systems. The absolute crucial point here is how this exact integer math restores true digital truth. By relying entirely on the perfectly deterministic ALU surveyor, we actually restore a principle of physics called Noether's theorem right into our computer architecture. Now, Noether's theorem gives us perfect symmetry and forensic reversibility. Because there are zero hidden approximations and no secret corporate seed tables involved, we can finally unblend the smoothie. We can perfectly trace our data backward, step by step, with absolute mathematical certainty, ensuring perfect provenance. Which leaves us with a final, truly provocative question to ponder today. As we continue to build the automated, AI-driven systems of tomorrow and literally hand over our financial and legal ledgers to machines, we have a huge choice to make about the foundation of our digital trust. Will you settle for the FPU gambler's best guess, letting invisible hardware passively blur the lines of reality? Or will you demand the perfectly traceable, deterministic blueprint of the ALU surveyor? Ultimately, the choice of how we command our silicon is entirely ours. Thanks so much for joining me on this explainer, and keep asking the hard questions about the systems you rely on.